Hi, I'm Michael Howard, and I'm going to talk about threat modeling as described in the SDL book. The goal of threat analysis and threat modeling process is pretty straightforward. It's to understand design flaws in our application. And in fact, if you look at the tools that are available out there, most of them are code scanning tools. And while code scanning tools are very valuable, they really offer nothing in the way of design, and the threat modeling process is really the only tool that we have, today anyway, that focuses exclusively on the design of a product. So the goal is to find security design flaws and to mitigate those threats and to understand how to mitigate the threats, but also how to reduce risk. And in fact, the real goal of threat modeling is ultimately to reduce the overall risk of the application. The threat modeling process has been updated quite substantially over the last year or so. In fact, if you've read Writing Secure Code or you've read Swiderski and Snyder's threat modeling book, we have actually updated the process quite substantially since those two books were written. A lot of it's basically been feedback from people using the threat modeling process. There's been two major areas of criticism in the threat modeling process, and quite valid criticisms. The first one was it was too much security expertise was required, and the second one was it was pretty subjective, especially in the calculation of risk. So we've done away with those two major problems in the updated process. So at a very, very high level, the first thing you need to do is define the scenarios. I'm going to explain all of these in detail, but you need to define the core scenarios that you're really interested in for your application. Next one is creating the data flow diagram. This is something that you need to do yourself. We can't do that for you. This is not an automatic process. This is something that you must actually do. And again, in the SDL book, we explain how to build data flow diagrams. So defining scenarios and building DFDs are both manual processes. Next is determining threat types, leveraging threat trees, and determining risk. These three steps are virtually automatic. Historically, they were manual processes, but now we've made them pretty much a rote process. So determining threat types is derived from the elements in the DFD. Leveraging threat trees, we used to say build threat trees. Well, the problem with building threat trees is that they require a lot of security expertise. And it turns out that there's actually a standard set of threat tree patterns that we use, and those are described in Chapter 22 in the book. And finally, determining risk. We used to say calculate risk, and this is where the subjective nature used to come in, where we'd expect people to calculate risk. Well, unless you're a security expert, you're not going to know what the risk calculation is or what the chance of attack is. And frankly, I don't really have much credence in that value, even from a security expert. So what we did is we took the calculation of the risk away and made it a set of heuristics instead. And again, I'll explain those in detail shortly. And finally, there's planning the actual mitigations themselves. Like how do you fix this? It's partly an automatic process and partly a manual process. The high-level techniques that you use are automatic, but the actual technologies that you use to mitigate the threats are very much up to you, and obviously that becomes a manual process. So the first thing is defining the scenarios and the background information for the application or the thing that you're modeling. The canonical example, and the example we've given many, many times, was during the developments of Windows Server 2003. We went back to the Internet Explorer team and said, okay, what are the threats when an admin is browsing the Internet from a domain controller? And we were really interested in those sets of threats. And I'm not talking about bugs here. I'm just talking about the fact that you have this level of functionality. How will attackers potentially try to exploit that functionality, and what are their attack vectors? And that led us to make a lot of changes in IE around mobile code, which is why we disabled most mobile code in IE. It was derived almost exclusively from the threat models. Another really good example is for a mobile device. There's a very critical scenario you need to think about, or not think about, depends whether it's in or out of the threat models, and that is the stolen device. Are you going to care about the stolen device scenario? Because if you are, the threat models are completely different. If you don't care about the stolen device scenario, then again, the threat models are very different. So it's really important that you constrain what scenarios you're really interested in. In the case of some threat modeling we've been doing recently with the MSN guys, one of the things we really looked at was is a rogue user in the data center, or are we going to rely on peripheral security and physical security, preventing rogue users from entering the data center. So again, you've got to think about all these scenarios and all these security preconditions and security assumptions about your application. And finally, you need to define your users. Who are the users? Are these administrators? Are these technical users? Are these home users? And the reason for doing that is this will help when it comes to thinking about how you're going to mitigate these threats, because obviously a threat that's mitigated with an extremely technical requirement may fail with an unsophisticated user. And so it's really important to understand who the users are. Never lose track of who your users really are and what their skills are. So the first thing you need to do is build a data flow diagram. DFDs have been around for a long, long time. There's nothing really new here. And the reason why we chose DFDs is for two main purposes, two main reasons. The first one is they're pretty simple. I'm a big believer in simplicity. I think if you give something, a technique or a technology to someone and they sort of get it, then they'll use it. You could give something to someone that's scientifically pure and mathematically sound, but they just don't get it. That's just a complete waste of time. And so DFDs are very simple. The average human being will understand them. The other nice thing about DFDs is they tell you where the data came from, hence the name data flow diagrams. And when it comes to understanding attacks, it's really important to understand where the data came from. And so DFDs give us that. So a DFD is just a graphical representation of how data enters and leaves and travels through your application. Don't confuse it with a class diagram or a function flow chart. They're not the same thing. I really want to stress the second set of bullet points, which is a good DFD is critical to the rest of the process. If you have a lousy DFD, you may as well not even bother doing threat modeling, because the rest of it will just be inaccurate. So spend as much time as humanly possible getting the data flow diagram accurate. At the highest level DFD, we have a thing called a context diagram. And this is an example context diagram of a sample application that I wrote, which is an integrity checker. If you're familiar with Tripwire, where you can run an application on a machine, and it'll tell you what files changed and so on. Well, this is a very similar idea. And the very highest level diagram is the context diagram, which is the application that you're modeling and then who interacts with that. So here you have a double-skinned circle, which is the application. That double-skinned circle is referred to as a complex process. In other words, it's a process with multiple logical processing inside it. The only users that use this are the administrators. No one else uses this application whatsoever. And that's represented by the rectangle at the bottom. And there are two arrows. One is the arrow going in, which is from the admin to the application, and that is the administrator instructing the application to do some kind of analysis. And then there's a data flow coming back from the application to the administrator, which is the integrity information itself, like what changed and so on. And the arrows are data flows, and they represent the data that flows through the system. Now you'll notice that the integrity application itself is a double-skinned circle, which means it's a complex process, which means that it contains multiple logical processing. Therefore, we need to drill down into that multiple or complex process. So the next diagram is a level 0 DFD, and you can see we're sort of exploding and looking deeper inside the application now. And so we have the admin, which is element number 1.0, communicating with a client console application 2.0. You'll notice that it's not a double-skin circle anymore. It's now a single-skin circle, or a single circle. And the reason for that is that's now one simple process. It's a bit of logical processing. That application reads configuration data, element 4.0, and it also reads and writes from the integrity baseline data, which is element 5.0. And there are data flows going from the application to the administrator, from the application to and from those two files that I just mentioned. The console application communicates with some host software that runs on every computer. And so they've got two data flows, one going from 2.0 to 3.0, another data flow going from 3.0 to 2.0. And the host integrity software reads data from the registry, reads data from the file system. It could read stuff from Active Directory, whatever you want. So the admin 1.0 instructs the admin console 2.0 to go and query a server, and then so there's a data flow from 2.0 to 3.0. It queries the server. The server does all the work it needs to do and sends the raw results back to the client, 2.0. Then it compares with the baseline information out of 5.0 to see whether anything changed or not. Now you notice there's some dashed lines here. This is something that we added to data flow diagrams, and it's particular to security, and we call them trust boundaries. And essentially where data moves from one level of trust to another, or you just don't trust the data, or it moves from one identity to another, there's a trust boundary there. So for example, here we have the data communicating between a local console and a remote console. So there's a trust boundary there because it's a network division. So you don't know what's on the other end. You just don't trust the other side. There's also a trust boundary between 3.0, which is the host integrity software, and the registry and the file system, because that data may be potentially have been compromised, and so we don't really trust it. So privilege boundaries are something that we added to data flow diagrams just to add more context to the actual diagram, so we understand where data is moving from low trust to high trust, or moving from points where you don't really trust the data. And this is a really important point, because as data moves from, say, one end of a trust boundary to another side of the trust boundary, it's important as data enters that system that you have very, very good checks of that data coming in, because you don't trust it. It's traversed a trust boundary. Every element in the data flow diagram is subject to one or more kinds of attack. And the attack is based upon the element type. So for example, you'll see here that the admin, which is an external entity, someone who communicates with the application, is subject to spoofing and repudiation. I'm going to talk about these shortly. But you can spoof a user, you can repudiate their transactions. A process is subject to absolutely all the STRIDE categories: spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Data flows and data stores are subject to tampering, information disclosure, and denial of service. But there is one little fly in the ointment. If you look at element 5.0, the integrity file, it stores logging data. If I'm an attacker, I'm probably going to try to cover my tracks, and the way I will do that is by whacking any logging data. And so that means if I can cover my tracks, I can repudiate my transaction, or the work that I did, the PEP work that I did. So in this case, the integrity file 5.0 is subject to repudiation threats as well. So I sort of touched on STRIDE. I want to go into STRIDE in a little bit more detail right now. STRIDE is just a taxonomy of threat types. It's looking at things from an attacker's perspective. If you're familiar with CIA, which is confidentiality, integrity, and availability, CIA are all security properties that you desire. STRIDE is a more fine-grained version of CIA that looks at it solely from the attacker's perspective. So the first one is spoofing. I can spoof somebody. I can spoof something. I can pretend to be Amazon.com. I mean, how do you really know that is Amazon.com and not Bob's Bookshop? I mean, how do you know that? It's a spoofing threat. You can also spoof a user. Hey, I'm Bill Gates. I mean, how do you know I'm not Bill? Or you can also spoof code. You know, this is ntdll.dll. I mean, how do you know it really is a valid ntdll.dll that came from Microsoft and is not a rogue? Tampering is when you can change data when you shouldn't be able to change it. Repudiation is the ability to go back on a transaction. The classic example is if you want to sell, say, 100 shares of Widget Corporation at $10 each. You go online, you go to your brokerage house, you select Widget Corporation, 100, you do a sell order at $10, and then click on Submit. And then finally, when the receipt comes back or the acknowledgement comes back from the brokerage house, in the intervening milliseconds, the stock goes up to $15 an item. So every stock item, rather than being $10, is now $15. So when the receipt comes back from the brokerage house, you say, well, I never made this order. I never made this order to sell these shares of Widget Corporation at $10 each. Now it's up to the brokerage house to prove that you actually did put a sell order in at this point in time. At this point in time, Widget Corporation was $10 a share, and so on. What's interesting about repudiation is humans repudiate. Software cannot repudiate. The way you repudiate is by dragging someone into court and presenting evidence in front of a judge or a jury, and then finally the ruling coming on either the plaintiff or the defendant. But it's all about showing evidence. Now, software may be able to provide some kind of evidence that could be used in a course of law. In many cases, I'm not going to get into the legal aspects of it, but that in many cases the value of the data is somewhat minimal. Often it's treated as hearsay, but again, I'm not going to get into that discussion right now. But repudiation is kind of interesting because there's a very important human element to repudiation. Next is information disclosure, which is the ability to view something when you shouldn't be able to view it. Denial of service is degrading or knocking out a service. And finally, elevation of privilege is when you can elevate from a lower level of privilege to a higher level. Now, historically, many people have thought about this as going from user to admin. And that's absolutely elevation of privilege. But there's more to it than that. If you can go from anonymous to user, user to power user to admin, local admin to domain admin, they're all sort of very small variants of elevation of privilege. But it's not just users. It could also be code. So, for example, if you were running a Java applet or a .NET Framework component, and you're granted a certain set of permissions, if there was some funky thing or a bug in the runtime that gave you other permissions, then that's elevation of privilege. Another good example is with zones in Internet Explorer. If you can actually bust out of a very restrictive zone through some URL parsing bug, for example, and all of a sudden you have more privileges, that mobile code has more privilege because of the zone that it's in, that's elevation of privilege as well. So it's not just looking at going from anonymous to admin, which is obviously very, very bad, but it's more than just user elevation of privilege. So now what we do, so I mentioned that we have this stride stuff, and we have all these data flow elements, data flow diagram elements, data flows, data stores, processes, and external entities. And what we do is we take the intersection of all the elements and stride. So we itemize all the data flows. So here are all the data flows listed from the integrity application. Here are all the data stores listed. Here are all the processes, and here are all the external entities. And what you do is you put a tick mark next to every element and what threat types apply to them. So, for example, for a data flow, they're subject to tampering, information disclosure, and denial of service. For processes, they're subject to everything, all the stride categories. Most importantly, you can only elevate against a process. Think about it. You can't elevate against a data flow. It makes no sense whatsoever. So you end up doing this little, creating this little matrix of all the DFD element types and all the stride categories. And each tick in here is a potential threat to the system. And each threat is governed by the conditions that make that threat possible. And this is where threat trees enter the picture. I sort of alluded to this earlier. Historically, we always thought that we always asked people to build their threat trees. And the description of a threat tree that we use is a list of security-related preconditions that can lead to the threat being real. Now, unless you're a security expert, you can't build these things. I mean, you really can't. We used to think you could. We were absolutely wrong. But what we did find out is by building lots of these threat trees is that they were basically threat tree patterns. So, for example, spoofing an external entity or a process, there's only some set of preconditions that can possibly exist. Tampering with a data store, again, there's only a bunch of preconditions that can really exist. So what we ended up doing was building these sort of canonical threat trees. So, for example, spoofing an interactor, which is another name for an external entity. To spoof a user, an external entity, there's many things you could do. One, you could obtain legitimate credentials, or you could falsify the credentials, or you could leverage a lousy authentication scheme, or there is no authentication scheme. So let's drill down a little bit further. Obtaining legitimate credentials, weak storage. So weak storage where? At the server or the client. So how is the data protected? How is the credential stored at the server or the client? Weak transit, how is the credential transmitted from one endpoint to the other? Weak change management. You may actually have very, very strong storage and strong transmission of the credential, but what happens when you come to change the credential? What's the policy and what's the process and the protocol that's used to actually change the credential? Falsifying the credentials, I could try to guess. I could try to guess your password. So the question we like to ask there is, so what's your password policy? How good is your password policy? Is there any notion of equivalence? For example, if you're using DES encryption keys, just as an example, a bad example, for a credential, well, there's actually the notion of what are called weak keys in DES, where one key can actually be decrypted with you can actually take some text, encrypt it with one key and decrypt it with another key, a different key, and get the same plain text back. And they're called the weak keys, the DES weak keys. There are also semi-weak keys as well. So again, you've got to ask yourself the question, is there the notion of a credential actually having the same value, or the same, representing the same credential, even though it's different? Next is leveraging a lousy authentication scheme like the null credential. You actually support anonymous connections. Okay, perhaps that's not a good thing. So the question is, do you support anonymous connections? And if the answer is yes, why? Downgrading the authentication scheme. This is a great one. You may actually have a current version that's extremely secure, version 2 really secure, but for backward compatibility, you have an older version 1 that's frankly lousy relative to today's threats. So you may support version 1 for backward compatibility. Well, as an attacker, I'm not going to attack version 2. I'm going to attack version 1. And all I'll do is I'll build a client that says, I don't do version 2, I only do version 1. And the server says, okay, and rolls back to a less secure authentication scheme. At this point, you can go and revisit this threat tree and start everything else again. So does version 2 have weak, so does version 1 of the authentication scheme have weak storage at the server or the client? Does it have weak transmission? Does it have weak change management? Is it easiest to guess these credentials? So downgrading the authentication scheme is actually a very interesting attack. The next one is predictable credentials. We've seen this a number of times in some cookie-based systems where they have a very, very strong password policy up front. And then they give you a policy give you a cookie afterwards, but the cookie is just an incrementing number. I mean, I'm not going to whack you. I'm not trying to guess your password. I'm going to just connect with my password, see what the cookie value is, connect again with a different session, see what the cookie value is. So, oh, that looks like it's an incrementing value. Well, what happens if I just set the cookie to the next value and then connect to the back-end server? Well, I don't need to enter your password. So that's because the credential has changed from being the password to the cookie, and the cookie's been predictable. The next one is tampering threats against the authentication process. I mean, imagine for a minute you had a process that validates that this binary is valid, and the way it determines that is by looking at the signature on the binary. Well, I'm not going to whack, some very well implemented crypto. What I'm going to do is I'm going to whack the process that actually says, hey, the signature on that binary is correct. That's what I'm going to do. So how is the authentication process protected? In some scenarios, this is actually a very, very valid attack scenario. So at this point, what you do is you then take the tampering threats against the process threat tree and start looking at that threat tree. So the threat trees can actually cascade. So that's just to give you an example, a very brief example of what these threat tree patterns look like. All the threat tree patterns are explained in gory detail in chapter 22 of the book. I want to point something out that's extremely important, and that is that you should always take important notice of information disclosure threats, and you should always look at the nature of the data that could be subverted or could be disclosed. If the data is confidential, sensitive, or personally identifiable information, and you have an information disclosure threat, you potentially have a privacy issue. And the net effect of that is it bumps up the risk. So calculating risk. This is very subjective. Historically, people have used calculations to calculate risk, like chance of attack, multiplied by potential damage is risk. Other people, we've used this thing called DREAD in the past, which is damage potential, reproducibility, exploitability, affected users, and discoverability. The problem with using numbers is they can be very subjective. And so we've tried to move away from using numbers. At Microsoft, there's still a lot of groups still using numbers. And we're not discouraging it. What we're saying is that the results, if they're consistent, that's fine. But the chance of them actually being consistent is pretty slim. And so what we're doing is moving away from using numbers to using a more heuristics-based mechanism, which is based on real-world rules of thumb. And we've derived these heuristics from the Microsoft Security Response Center rankings. So this is actually described, again, in the book. I think it's in Chapter 9 on the risk analysis chapter. So, for example, if you have a denial of service against a server process, and it's a remote denial of service, and it's not authenticated, and the server is now dead, That's important. Or a certain level of criticality. And the reason for doing that is we can actually say that anything above this threshold you must fix, and anything below this threshold you can consider for a future version, or perhaps just remove that functionality, or just warn the user about these particular scenarios. So, the nice thing about this is there's no guesswork. The guesswork has been taken away completely. So finally, you've got this stack-ranked list of threats, and you got like spoofing threats against processes, and tampering threats against processes, and denial of service threats against processes, and data stores, and so on and so forth. So how do you fix it? Well, there's a bunch of ways of fixing it. You could decide to remove that feature from the product altogether. That's actually, in some instances, that's actually a very valid remedy. You may think that this is really high risk. The chance of fixing this in a correct way is very slim. And the risk to the user is extremely high, even after the fix. You know what? We're just not even going to do it. Not even going to bother building that feature. And that's the beauty of the threat modeling process, is because it's done very, very early in the process, or should be done very early in the process. You can find these issues very early on and decide not even to build that feature. So you save all the time. Compare that in the past, where you may have built the feature anyway, spent 15,000 hours designing, building, testing, documenting it, and then just before you ship, you think, oops. This looks kind of bad, and then so you remove it from the product, and in the meantime you spent 15,000 hours building this thing. You yank it from the product. 3 other features in the product depend on that feature being there. It's now gone. They've all now got regressions, and the clock's still ticking until you ship the product. So the beauty of doing the threat modeling exercise very early on is you can find a lot of these issues very early on and decide not to even build certain things, which is a great time saver. In some instances, you may decide to warn the user, say, hey, do you really want to do this action? Be very careful of warning the user too many times. Don't interpret what I say the wrong way, but users in general don't make good security trust decisions. And it's not because they're stupid. That's not the case whatsoever. It's just people often don't understand the ramifications of some geeky thing. Do you want to install this root certificate with this SHA-1 hash and this MD5 hash? Yeah, sure. Users don't even know what the dialog means. Eventually, they get to a point where they see a dialog pops up, and they just read, "Do you want to get your job done?" Click yes. So don't keep warning users all the time to make trust decisions. Because eventually they'll just become wary and weary, actually, of those dialog boxes and just say, yes, get out of my face. Just annoys users. So one thing I watch out for is when I'm looking at mitigations is, are you relying on the user making a trust decision? And that's fine in some cases, but don't have every mitigation as, well, get user consent, get user consent, get user consent. Because that really what you're doing is you're pushing off the security of your product, security and privacy of your product, to the user, when you should be doing as much as possible in the product. The third mitigation is to actually mitigate it with technology. And we have these very, very high-level techniques that you can apply. Remember I said very, very early on that when it comes to planning the mitigations, it's sort of partly manual and partly automatic. The automatic part is the actual technique that you can apply. So if you have a spoofing threat against a process, you can mitigate that with authentication. Now, that's a technique. The technology you apply depends on many, many factors. For example, does it even solve the problem? If you were to use it, would your users understand how to deploy it? Do you even have the skills to build this? Do the platforms that you want to use actually support this technology? So I like to say, when I'm looking at any kind of technology to mitigate a threat, is could you use it? Would you use it? Could you being, does it really solve the problem? Would you being, is it even usable? Here's a good example. Let's say you have a spoofing threat against a web server. This Amazon.com example I gave before. It's a spoofing threat. It could be Bob's Bookshop. How do you know it's Amazon.com and not Bob's Bookshop? So when you give your credit card information to Amazon.com, how do you know it's going to Amazon.com and not to Bob? Well, there's an authentication step that goes on. That has to go on there to make sure it really is Amazon.com. So that's authentication. Okay, that's fine. So we have a bucket load of authentication technologies at our disposal. We have things like basic authentication and digest authentication. So the question is, could you use either of those technologies? And the answer is no, because they don't provide server authentication. Could you use Windows authentication, NTLM? And the answer again is no, because NTLM only does client authentication. It doesn't do server authentication. Amazon.com would know it's you, but you would not know it's Amazon.com, which is not the threat that we're worried about. We're worried about knowing whether this is Amazon.com. Could you use Kerberos? Well, the answer is technically yes. Kerberos does provide client and server authentication. Would you? Not on your life. There's no way. I can't imagine Amazon.com building up a whole key distribution center, opening up port UDP 88 on the internet. I mean, that's like, hackers come get me. There's no way they would do that. Could you use IPsec? It's an authentication set. It has an authentication built into it. Yes, you could. It does provide, technically provide client and server authentication of the computer, not of the users. But that's fine. We want to verify this is actually a box that's owned by Amazon.com. So could you use it? Technically, yes. Would you? I doubt it very much. I doubt Amazon.com will start deploying IPsec policy to all their customers. Next one is SSL, TLS, Secure Sockets Layer. Could you use that? Yeah, it does provide server authentication by default. Would you use it? Yeah, it's built into everyone's browser, and we've taught an entire generation of people to look for that lock or that key icon to know that it's actually Amazon.com. So, yeah, we have an authentication technique, and the technology that we would use here is SSL, and guess what? That's exactly what Amazon.com use. For tampering, we have integrity technologies, things like access control lists, things like message authentication codes, hashes, digital signatures. Repudiation, the mitigation features are non-repudiation, which is kind of helpful. But really it's a grouping of other techniques like authentication, integrity technologies. You may also include trusted third-party timestamping services and so on. Actually, a really good example of a timestamping service that you use every single day and don't realize it is the Postal Service. If you need to put something in the mail by a certain date, there is this trusted third party, this disinterested trusted third party called the U.S. Postal Service, or the Postal Service of your country. And they stamp the envelope with the date they receive it. And that's an example of an intermediary that's not interested in the sender or the receiver, but it's an intermediary that the transaction can go through. For information disclosure, you have confidentiality technologies like, again, access control list or permissions. Encryption is another good example of confidentiality technologies. For denial of service, you have availability technologies like quotas and throttling and so on. And finally, for elevation of privilege, you have authorization technologies. For example, are you actually allowed to perform this privileged action? And if the answer is no, then it fails. So there's some very, very broad techniques that you can apply. And that's automatic. And then finally, from those techniques, you need to choose the appropriate technology to mitigate that specific threat. The other really cool thing about the data flow diagram is it aids in the code review process. So if you have a data flow diagram, you've got to realize that the bad guys will always access the code along the line of least resistance. Let's assume for a minute you have two data paths that go through the two major code paths that go through the code. One requires anonymous privilege. In other words, anyone can actually exercise that code. Versus another one that requires you must be a valid user. Now, if you're the bad guy, where are you going to go? Well, you're going to go across the anonymous data path, and the reason for that is because you can. That's it. In the blue path, you need to be a valid user. You need to have a valid user account on the box, which may be in some scenarios an absolutely valid attack. But if I was a bad guy, I'm going to go across the anonymous path because I can. There's nothing there stopping me. The cool thing about this is it allows the developers, when they're looking at their code, to say, man, I've got this anonymous code path through my code, and I really don't want that there. And so you can go back to the design team and say, look, I want you to reduce my attack surface by requiring authentication. And so the developers or the designers can then add an authentication step at the beginning, which will change this from an anonymous path to a user path. But the critical message here is if you're a developer, you should look at the data flow diagram, you should look at all your anonymous code paths and review all the code along the anonymous code path, because that code has to be extremely good, because anyone can exercise that code path. And if there's a vulnerability in that code, anyone can make that code fail, which can lead to disastrous consequences. So review your code along the anonymous code paths, and finally, if you think you have too many, or you just don't like the fact that you have these anonymous paths, go back to the design team and say, hey, look, I want authentication here. That way it will reduce your attack surface substantially. But still do the code review as well. Next is testing the threats. Every single threat in the threat model must be tested. Historically we found that most security testers are not good security testers. Sorry, most testers are not good security testers. Well, the threat model can help drive a lot of that process. So first and foremost, every single threat needs to be tested. And there's black hat tests and white hat tests. So white hat tests are proving the defenses work, and black hat testing is proving they don't, and that's actually a lot more fun. But the next thing is, so how do you do these tests? Well, it's all dependent upon the actual threat type. So if you have a spoofing threat, you can mitigate that with authentication. You can attack authentication techniques in very well-known ways. So, for example, you can do brute force attacks. You can do downgrade attacks. You can try to look for the credentials, where the credentials are stored, and see how well they're protected. Now, you may be thinking to yourself, hang on a minute, that sounds a lot like what I just described in the threat tree. Absolutely. The leaf nodes in the threat tree not only help you think about some of the design questions, but also help you think about how to do the tests. And in fact, in Chapter 22, when we show all these threat trees, we also explain how you can design against these leaf nodes in the threat trees, and also how you can do security testing against those leaf nodes. So to wrap up, no design is complete without a threat model in place. I mean, just think about it for a minute. How can the design be complete if the design doesn't represent the threats to the system? I mean, the design can't be complete. Watch out for those anonymous data paths, because that's where the bad guys go. Every threat in the threat model must be tested. Watch out for all your information disclosure threats. Are there any privacy issues underneath there? And finally, watch out for elevated processes. I mean, does this process have to run in some kind of elevated identity? Because if the answer is yes, it has to for these reasons, then if I can make that fail and I'm a lower privileged user, then I may be able to actually elevate my privilege on the box, which would not be good. And finally, use the threat modeling tool. At the time of, while this has been recorded, there's actually 2 threat modeling tools available. There's the old one that came out a long time ago with Swiderski and Snyder's book. There's now a newer version that's put out by an internal development team at Microsoft who work mainly with customers. That's actually a beta 2 that's available right now. So if you go to msdn.microsoft.com, WAC Security, you can find a link to that threat modeling tool.